In this video, we're going to be talking about how we write the formulas of ionic compounds. So this is a topic that should be familiar from Chem 1, so hopefully this will be kind of an easy refresher for you. So we know that ionic compounds consist of a cation and an anion. For the purposes of this class, there will always be only one kind of cation and one kind of anion. There may be more than one of the same type in order to balance the charge, but more on that in a moment. But all of the cations will be the same, all of the anions will be the same. So remember that our cation is positively charged, and our anion is negatively charged. So ionic compounds are always a combination of a cation and an anion. By convention, the cation is what's written first in the formula. So if you're looking at the formula for an ionic compound, if you recognize it as an ionic compound, you know that the thing written first has a positive charge, the thing written second has a negative charge. So for example, most typical ionic compound that we think of is NaCl, or sodium chloride. We put the sodium first because that is the cation, and we put the chloride second because that is the anion. So that is always going to be the case. So for ionic compounds, you should always kind of know which goes first. If you're writing the formula yourself, or if you're looking at a formula, that is a piece of information that you can get from it. So the other thing that we know about ionic compounds is that the total charge on any ionic compound must add up to 0. So ionic compounds are composed of charged particles, but overall they're neutral. When you add up all of the positives and negatives, they balance each other out, and you get a total charge of 0. So what happens if, say, our cation has a positive 2 charge and our anion has a negative 1? We just adjust the numbers of each of our ions with subscripts in our formula in order to make it so. So we'll adjust the number of each ion in our formula by changing subscripts to make this true, to make the total charge 0. So we need to be able to figure out how to do this. And one of the many things that the periodic table can help us with is predicting what charge on an ion is likely to form for a particular element. So we're going to be using the periodic table to do that. So we can't predict every element, but we can for quite a few. So if we take a look at the periodic table, I've got one down here. There are a few sections to be aware of. So the middle bit here, the transition metals, we really can't predict what their charges are going to be. That's not very legible. Trying to color code here. Usually, there's more than one possible charge for any given element. So we cannot predict just from the element alone what our charge is going to be. We need some more information. But for much of the rest of the periodic table, we can. So starting from the left here, our first column, the alkali metals, and also hydrogen, generally tends to form ions with a +1 charge. So that applies to the whole column. Occasionally, hydrogen can be -1, but it's really, really uncommon. So unless it's a special situation, we usually consider hydrogen to be +1. In a few weird cases, it can be -1. In the next column here, writing utensil, these tend to form a +2 charge. So the reason for these charges comes back to the electronic structure, comes back to the orbitals, that our atoms want to have a full valence shell. So in the case of the first column here, these guys have one valence electron. So they have one electron that's way farther out than the rest of their electrons, than their core electrons. So that one valence electron is really, really easy to remove. And when you get rid of it, now they have a full valence shell underneath. So by losing one electron or gaining a +1 charge, they get that stabilized valence shell that they want. So that's really the reasoning behind all of these. For this second column, you have to lose 2 valence electrons in order for that to be true. Moving along over here, elements in this column generally form a +3 charge when they form ions. The next column you might think is going to be +4, and it kind of is in some cases, but for the most part, this column actually doesn't form ions. So these first 3 elements really don't form ions to any appreciable extent. No ions. The ones that do are down below. So tin and lead in particular, fluorovium down the bottom is new enough and not well studied enough that we don't really know what it does in terms of ions. But tin and lead can actually form either +2 or +4 charges when they form ions in ionic compounds. The next column tends to form -3, so now we're going in the other direction because it's easier for this to gain 3 electrons to get its filled valence shell, as opposed to going in the other direction, it would have to lose 5. So it's closer to a filled valence shell by gaining than losing, so that is what it's going to do. So that column, the nitrogen family, usually forms ions of -3. What color haven't I used yet? It's purple. The oxygen family usually forms -2. The halogens usually form -1. And then the noble gases are already stable. They already have a filled valence shell. So these guys also don't generally form ions. So we can use the periodic table in this way to either help us predict that, like, oh, oxygen is in this group, that group usually forms -2. So we can use it to help us predict for certain elements, or in some cases help us know that we can't know just by the element alone. If I'm like, what's the charge on iron? You don't know. It could be +2 or it could be +3 in that particular case, but you don't need to know that. You can just recognize that it's uncertain. You need more information. But we can use this as a tool to help us correctly write formulas for ionic compounds. So if we want to do that, move this off to the side. Oh no, that's not what I wanted. We'll just leave that where it is. If we want to write the formulas for some ionic compounds, I'll just do one or two examples. If we want to write the formula for the compound that forms between, let's say, potassium and sulfur, we can find those two things on the periodic table. Potassium is here. It likes to have a +1 charge, generally. Sulfur is over here. That family likes to have a -2 charge. So that means for every one positive, we have 2 negatives if we just stick one of each ion together. So in order for our total to come out to 0, we're going to need 2 positives. We're going to need 2 potassium ions for each sulfur. So we know that we want to write the cation first in our formula, followed by the anion. So potassium is K and sulfur is S. And then we put in subscripts to indicate how many of each we have. So we need 2 potassium, so we'll put the subscript 2 after the K, and that is the correct formula for potassium sulfide. Let's do one more. Let's do calcium. Nah. Let's do aluminum. Oops. And oxygen. So if we look back to our periodic table, we're looking for aluminum, which is over here, and its family usually likes to have a +3. And oxygen is in the same family as sulfur, so that likes to have a -2. So aluminum +3, oxygen -2. So figuring how to get these to balance out, we can't have fractional atoms. We need our subscripts to always be integers. So the simplest way that we can do this is to have 2 aluminum ions paired with 3 oxide ions, so that we have a total of 6 positives. +3 times 2 is +6, and 6 negatives. -2 times 3 is -6, so that our total ends up once again at 0. So writing our formula, cation first, anion second, we'll have 2 aluminum and 3 oxygen. So our formula is Al2O3.